Hi, my friends. How's everybody doing? Let's get started with lesson 3 here. A couple of quick classroom announcements before we get started. I've gotten quite a few questions regarding the assignment for lesson 2, and which will continue on for lesson 3. If you're not sure where the questions are that you'll be answering on the Google Doc, they are in the Equilibrium worksheet PDF that's posted. So if you go to the section in classwork that's labeled equilibrium, it should be the only topic we have at this point. You'll see the equilibrium notes that are filled in, not filled in, and you'll see an equilibrium worksheet packet PDF. So the work that you did for lesson 2 is in the first 3 pages, and the work that you're doing for lesson 3 is in the first 3 pages. I put on the Google Doc exactly the questions you will be doing for each of those stresses that we're talking about. And you just type in your answer. Your only possible answers are going to be left, right, or no change. And I'll give you a hint. For temperature, it should only be left and right. We didn't talk about any no change situations. That'll come up with pressure. All right, so 30-second recap. We talked about equilibrium, the 2 definitions of equilibrium. The concentration of the reactants and the products are constant. It means they no longer change. Okay, they are flatlining for concentration. And the rate of the forward reaction equals the rate of the reverse reaction, which basically means that whatever work is being done in the forward direction is also being done in the reverse at the same exact time and the same exact speed. So therefore, whatever is being done is also being undone. All right, so that's why you don't see any changes. Let's see, phase equilibrium or physical equilibrium. That is when you have an equilibrium between 2 phases. So melting and freezing, boiling and condensation. This little graph should look familiar. Our heating or cooling curves, those flat lines, those are the temperatures at which you can have 2 phases present. And don't forget about solution equilibrium, which is a fancy way of saying a saturated solution. We discussed what a stress and a shift was. So a stress is some type of change that can be applied to a reaction at equilibrium. And when that stress is applied, the reaction will shift. All right, so the 3 stresses: changing the temperature, changing the concentration, adding or taking away a substance, and then changing the pressure, which will only affect gases. When we say a reaction shifts, we are talking about what direction are we pushing the reaction towards. So depending on the stress, if a reaction shifts to the right side, at the bottom here, we talked about how you will be pushing that reaction towards that right side and making more of whatever's on the right by using up whatever's on the left. And then just the opposite. If we do something to make a reaction shift to the left, we're going to make more of whatever's on the left side by using up whatever's on the right. All right, so we would say if I shift to the left, I would say the concentration of H2 and Cl2 will increase while the concentration of HCl decreases. All right, temperature was our first stress that we talked about. Increasing and decreasing the temperature, you need to know your endothermic and exothermic directions. So we discussed this in many other topics, and I filled them in for the 2 examples here. When you have heat written on the reactant side, that means going forward it is endothermic. Right? When you have heat written on the product side, going forward is exothermic. Well, with equilibrium, we can now go in reverse. So if the forward reaction is endothermic, the reverse is exo, and vice versa. Increasing the temperature will always favor or push in the direction of the endothermic reaction. So increasing the temperature for this first example makes the reaction shift to the right, because that forward reaction is endothermic, while decreasing the temperature makes it shift to the left. Okay, Over here, we follow the same rules, but I have the heat written on the product side, making the forward reaction exothermic. All right, so increasing the temperature, it no longer shifts it to the right because it is no longer endothermic going forward. The endothermic direction is going towards the left. So increasing the temperature shifts that reaction to the left side, making it, the reaction shifts to the left side. So we will be increasing the concentration of X. Decreasing the temperature shifts in the exothermic direction, which would be towards the right side. We would be making more of whatever's on the right. So we make more of Y and Z. And we added on that an extension to that question would be, what would happen to the concentration of X? If I'm shifting to the right and making more of Y and Z, that means this is going to decrease because I'm using it up. Okay, so that's just a recap of what we've done so far. Now we are going to get started with concentration and pressure. Okay, just want to check my time here. Okay, so here we go, concentration. I'm going to just zoom in on this a little bit. Okay, so concentration. When we say concentration, we are adding more substance or removing substance. Okay, so that's the first thing. Adding more substance or removing substance. I'll give you a second to jot that down. Okay, so if we say that we're increasing the concentration of something, it means we just added more of it. If we're decreasing the concentration of something, we're taking some of it away. All right, so it's basically like saying the amount. Okay, so I'll just put that like in parentheses, the amount. So what I want you to think about, if you just, it kind of makes sense if you think about what's actually happening here. If I increase the concentration of a substance, any substance in the reaction, it's going to shift to the opposite side. All right, so think about what that means. If I have a bunch of reactants and I add more reactants, I'm going to make more product. I'm going to shift that reaction to the opposite side. So if I'm adding stuff on the left side, we're going to shift to the right side and make more of whatever's on the right side. Then if I decrease the concentration of something, if I take something away, the reaction is going to shift to that side of what we took away, of what we decreased, because it wants to replace what was taken away or what was lost. So I put this little hint over here, up and away. Okay, up and away. And we'll get to that. We're going to come back to this in a little bit, but you might want to just jot that down now. All right, up and away. And the other thing we need to know is the notation for concentration. The notation for concentration are squared brackets. And when you see those brackets written around a formula, we're talking about the concentration of that formula. All right, so let's take a look here. Increasing the concentration of A, all right, and again, I'm going to highlight my stress, okay? We are increasing the concentration of A. That's our stress. The reaction is going to shift to what side? Well, here's the up and away I was talking about. If I increase, if this goes up, we go up and away to the other side. So whatever concentration increases, you will shift away from it to the opposite side. So if I increase the concentration of A, if I add more A to this reaction, I am now going to get more collisions between A and B, and I'm going to make more C. All right, that's the shift to the right. So we're going to shift to the right side. And by shifting to the right side, well, what's on the right side? Substance C. So we are going to produce more C. Okay, so by increasing the concentration of A, we force that reaction to shift to the right side. Now, decreasing the concentration of A. Let's say we came along and took away some of the A. All right, well, if I take something away, the reaction is going to want to replace it. It wants to replace what was removed. So if I took away some of substance A, this reaction will shift to the left. All right, the C will break down into A and B in order to replace the A that was lost. All right, so decreasing the concentration of something shifts it to that side. So decreasing the concentration of A will shift it to the left side. All right, and you will be producing more of A and B. Okay, you'll be producing more of A and B. Now let's just talk about a question from the other side. If I increase the concentration or decrease the concentration of C, which is on our product side. All right, if I increase the concentration of C, well, again, increasing, that means it's going up. Think up. That was an awful arrow. Up and away. If I increase the concentration of C, which is on the right side, we're going to shift to the left side. And then if I decrease the concentration of C, if I take some of that away, then the reaction is going to shift to the right and try to replace it. So decreasing the concentration of C shifts the reaction to the right. Okay, so we have to remember what a shift is. That's probably the one thing that people forget. Like what's actually happening when you shift? When you shift to a side, you make more of whatever's on that side you're shifting towards. That's all a reaction can do, is it can go forward or backwards. So again, if we do something to change the equilibrium, the reaction is going to shift to one side or the other in order to regain a new equilibrium. All right, so again, for concentration, just think up and away. Okay, now pressure. Pressure is the easy one, all right? We saved the best for last here. Now pressure, let's get the notes down. A question is going to ask you, how does this reaction shift when you increase or decrease the pressure of a gaseous reaction? And when we say a gaseous reaction, we are meaning that they are all gases. All gases in the reaction. Every single thing is in the gas phase. So if you see a reaction that does not have all gases, pressure will not affect equilibrium. Okay, it has to be all gases. Sorry, guys, my son just came into the room. Wait, buddy. Okay. So here we go. Pressure will shift a reaction depending on the number of moles that are in the reaction. So increasing the pressure, the rule is that you increase the pressure, you shift the reaction to the side that has less moles of gas. And if you remember, the moles are the coefficients. Here we go. So right here, and right here. Those are your moles. Okay, remember we did mole ratios and balancing equations and all that. So now we're going to add up the moles on the left side of the reaction and the moles on the right side of the reaction. All right, so again, the rule is increase the pressure, shift to the side that has the less moles of gas. Well, I have 5 and I have 3. I think it's safe to say that everybody can see that 5 is greater than 3. All right, so the reaction is going to want to make more of whatever it doesn't have as much of. So if the pressure is increased, the reaction will shift to the side with less moles. which is the right side. If the pressure is decreased, the reaction will shift to the left. Okay, and again, this is our stress. Increasing and decreasing the pressure is our stress. I mentioned in the Zoom, or actually I mentioned it before also with the homework, this is where you will have no effect as a possible answer, because you could have the same number of moles on either side. And if that's the case, well, you don't have one side that has more or less than the other, so you can't shift to a side that has less moles of gas. If the moles of gas are equal, there will be no effects. Okay, so if the moles of gas are equal, your answer is no effect or no change. Actually, I lied. One more thing that's even easier than pressure. Catalysts do not cause a shift. Okay? We talked about catalysts. They will only increase the reaction rate by decreasing the activation energy. That was the whole thing with this. Okay, with our potential energy diagram. So when you add a catalyst, I'll draw it in green, that activation energy decreases and it increases the rate of reaction, but that's the rate of reaction. That's how fast a reaction goes. That has nothing to do with equilibrium. Okay, so catalysts do not affect the equilibrium. That again would be a no change or no effect. Okay, just want to take a quick look here. Good. All right. So this is a little bit longer than I had hoped for. I know we had a couple of announcements at the beginning. You have the homework. These were the homework pages. All right, this is part of the worksheets. So again, lesson 2 and lesson 3, you're doing numbers 1 through 7 here. All right, you have 1 and 2 on the front, 3, 4, 5, 6, and 7. Your Google Doc has a spot for the correct question, going by letters, with the question number, depending on the stress. So temperature, concentration, or pressure. All right, so you follow along exactly with what the questions tell you on the Google Doc, which order to go in, and that will group your stresses all together. All right, so that way you won't, mix up the different stresses, and you'll kind of be doing the same thing over and over again. What I'll also probably do in the next day or two is do a quick little review. In fact, on Monday's lesson is going to be going through some of the worksheets. So I'll tell you guys which worksheets we're going to do as we go through them. So if you could just have that PDF file up on your screen, I'll be going through each page, and you can just copy down the questions as we go through if you'd like to do that. So it'll be kind of like a review day on Monday. And also don't forget that we have our Zoom call on Monday at 12 o'clock for extra help. So this is where you want to ask questions. I would say try to do Monday's work before noon, so that way you can go into extra help with questions if you'd like. And I'll probably have answer keys posted as well, so you can get as much practice in as you can before the extra help time. All right, guys. Again, hope all is well. Feel free to get in touch with Reminds or email if you need. And I hope everyone is doing great. Take care.